Hi, we're ready for our third lesson in this polynomial chapter. Today we're going to talk about what makes a polynomial function and how their graphs behave. So to get us started, a polynomial function is one whose exponents are positive integers. Exponents are positive integers. And whose coefficients are real numbers. Coefficients, so those are the coefficient are real numbers. A coefficient, of course, is the number that's a multiplier, so like this -3 is a coefficient. All right, so I'd love to have you take a look at these and just based on those two components decide for these 1, 2, 3, 4, 5, 6 functions that are listed, are they polynomial functions or not? So we're going to be looking for expressions whose exponents are all positive integers and whose coefficients are real numbers. And I would ask you to take a look at g of x here. We have -3x to the 5th plus the square root of 2 times x. I want to just remind you that the exponent on x is 1 here, so we do fit the positive integers for exponents. Are our coefficients -3 and square root of 2 real numbers? Yep, both are. This is irrational, but that's still real, so this is a polynomial. H of x has a coefficient of -3 and of root 2. We know the coefficients are okay there, they're both real numbers. This exponent is 2, and boy, if I'm remembering right, that square root of x is the same thing as x to the 1/2. 1/2 is not an integer, so h of x, not so much. All right, what do you think? What about f of x? Real number coefficient? Exponent? Yeah, this doesn't have, though, an exponent, except if we remember that x to the 0th power is still same thing as 1. Now exponents are positive integers, so we're good there. Actually, 0 is unsigned, but this one is good too. J of x, I hope you already have made your decision. This one is no good. That exponent is not an integer, so that cannot be a polynomial function. Now this is interesting. -3 over x squared. The problem, I think, what I'm thinking about is that exponent in the denominator down there. If we were to write that so that it was up on the ground floor, that would look like this, x to the -2nd, and that is not positive, so this one is no good either. Here we have 2x to the 3rd minus pi, and I'm hoping that y'all are looking at it and thinking, yep, constant's okay. Yeah, this is a polynomial function. So we had 3 yeses and 3 no's in there. Good. So polynomial functions of degree 2 or higher have graphs that are smooth curves and are continuous. Smooth curves and are continuous. Now I want to talk just a tiny bit about what those things mean. Continuous. Curve, yes. We should never in a polynomial see, oh, I don't want to say that, never is a long time. We should look at no gaps in here. We shouldn't, in a polynomial, we shouldn't have it start here and then take a jump and go that way. No good. Smooth curves and continuous. You should be able to trace over a polynomial without ever lifting your pen. There shouldn't be any gaps or holes in them. And the two polynomial functions that are pictured here, a cubic with a multiplier of 0.25 and a degree 4 polynomial with a leading coefficient of 0.75. Degree 4, and look at the end behavior there. All right, let's pop on. All right, the leading coefficient test predicts a polynomial's end behavior. So I said a moment ago, I was getting ahead of myself, I guess. End behavior. You'll recognize that term from your study in algebra. In this so we have 4 types of end behavior displayed here. The things that we're going to be looking at are the sign on the leading coefficient and the degree of the polynomial. So this one has an odd degree. The leading coefficient is positive here. Now, I know that some of you will remember from your algebra classes that we describe this kind of behavior as down up. Okay, that is a shortcut, folks, and I'd like us to get used to looking at it in the technical terms, perhaps. So, as x approaches, the arrow means goes to or approaches. As x approaches negative infinity, so when x is getting very small, in this one, y is also approaching negative infinity. That is, it's going down. As x approaches positive infinity, y approaches positive infinity. And from here, it's not a big leap to say we're looking at a down-up behavior. Okay, we usually talk about the negative x's first and then the positive. Our next model is also an odd exponent, so an odd degree. You can tell that because you have the whole ribbony behavior, or one way to think about it, I call this ribbon behavior, but you have one branch that goes down and one that goes up eventually. Odd degree, this one has a negative leading coefficient, and you can see what happens there. Remember, the negative leading coefficient flips over the x-axis, so the branch that was down is now up. And as we talk about end behaviors here, as x goes to negative infinity, in this one, y is going to positive infinity. Okay? When x gets small, y gets big. As x is going to positive infinity, y is going to negative infinity. Our next model has up end behavior. Oh yeah, I didn't say that here, but I could have. This one is an up-down model. Up-down, odd degree with negative leading coefficient. This one has even degree. And this one is a positive leading coefficient. And you will see that as x approaches negative infinity, that is when x gets very small, y is getting very big. Okay, up, 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 up. As x approaches positive infinity, y also is going up toward infinity. So we have up behavior on this one. On this guy, even degree, can tell this because at their ends, this function is both going in the same direction. This time happens to be going down, which means we have a negative leading coefficient on this one. And as far as writing the end behaviors, as x goes to negative infinity here, y goes to negative infinity. And as x goes to positive infinity, so x gets really big, y gets very small, negative infinity. So those are our 4 models for end behavior, and I'd love to have you apply it to this rule. I would point out to you, though, this is not all multiplied out. So before you start making up your mind, you got to be thinking about what the power on x will be, whether it will be even or odd, and the sign of the leading coefficient. So if you were to multiply here, no negatives in front of the x's, I think we're positive here. We're either going to be here or we're going to be here. To determine which one, we just have to think about how many powers of x there will be. 3 from there, 1 from there, and 1 from there. So this is going to be a 5th degree. A 5th degree polynomial with a positive leading coefficient. And we should be able to talk about its end behaviors then. We've got an odd degree and a positive leading coefficient. We are under our first model over here. So we are going to have, as x goes to negative infinity, y goes to negative infinity. As x goes to infinity, positive, y also goes to positive infinity. Now some of you I know are going to be asking me, is it okay if I just write down, up? Or many people, so this would have down, up, and behavior. Some of you will have used arrows to show that before, down, up. I am familiar with all of these things. I will tell you our textbook is looking for this. So in tests and quizzes, you should be prepared to look at that function type notation. All right, so end behavior. Next, we'd like to think about finding the zeros for polynomial functions. And I'll tell you that there are several ways that we can accomplish this. The first way that I'm going to look at here, it says to do it algebraically, setting f of x equal to 0 and solving for x. So as you take a look at this one, that would mean 0 has to equal x cubed plus 2x squared minus 4x minus 8. And I would ask you to think about this. Do we know how to factor a cubic? Yes and no. Some of them can be factored. And if this one, if it's possible, you should think about factoring by grouping, unless you recognize a cubic pattern. And this one doesn't look like any pattern that I know. But if we can factor this by grouping, that'll help us. So think about that. You draw out the greatest common factor in here, and those can both give up an x squared. What would be left over? Well, x squared goes into x cubed x times. It goes into 2x squared 2 times. The biggest thing that both of these can give up is a negative 4. And if we divide negative 4 into negative 4x, we get an x. Negative 4 goes into 8, positive 2 times. That's good news, folks, because each of these two terms now has an x plus 2 in them. So our factored form for this would be x plus 2 times x squared minus 4. And I know some of you are thinking, hold everything, because that still factors. That's a perfect square, so is that. We can apply that difference of squares here. X plus 2 is one of the factors. Difference of squares goes square root of the first with the square root of the second, once positive and once negative. So our fully factored form is x plus 2 times x plus 2 times x minus 2. As far as finding the zeros, the x values that make those things true, we have x plus 2 factored twice. In order for that to be equal to 0, x must be negative 2. Since we had that twice, we call that a multiplicity of 2. That is, it happens more than once. That root happens more than once. Multiplicity 2, because there were 2 like that. And we have an x of positive 2 here. A second method for finding zeros in polynomial functions is to use your calculator, although I would challenge some of you. This one is factorable if you want to give that a try. But I am going to pull up my calculator, and we'll look at that in just a moment. Go ahead and enter that function, x raised to the 4th power minus 4x squared. Good, and I believe the standard viewing window will be good for us to see this. So I'm going to go ahead and hit enter. And there's our graph in all its beauty. It does exactly what it should. It's an even exponent, so it has that up end behavior. It is a positive leading coefficient, so we're looking at an upwards opening. And we're to find the zeros. And just by inspecting, it looks like they should be at negative 2, at 0, and at positive 2. But I just want to run through the process for doing that one more time. Menu on this calculator, then it is Analyze Graph, and 0. If you're on the TI 84 or 83, second trace and 0. We set boundaries on either side of a given 0. That one does happen at negative 2. I'm going to come over here and do the same thing on the other side. Menu, Analyze, 0. Set a boundary, set a boundary. So there are 2 of our 4 zeros that we would expect. It looks like it hits right here at 0, and I'm going to check that one as well. Menu, Analyze, 0. And to the left of it, to the right of it, and sure enough, at 0, 0, you also have a 0. So we have 3 zeros for this polynomial, and they happen at positive and negative 2, and at 0. However, I know that there are supposed to be 4 zeros if I have a 4th degree polynomial. So I want to just ask you to think about what we saw. It looked kind of like that, and this was a 0 in that thing. You might think about it as hitting it once on the way up, once on the way down, although that's not mathematically correct. But what does happen is that 0 is a 0 of this particular polynomial twice, or it has a multiplicity of 2. Now we've used that term, multiplicity 2, a couple of times. A 0 is said to have multiplicity if it is repeated. Multiplicity if it is repeated. All right, very good. So we solved by factoring, we solved with our calculator. Let's look on and see what we have. Just some helpful tips here. If a 0 has even multiplicity, okay, that means a multiplicity of 2, then you will be assured that the function hits at that point and bounces back. In the one that we looked at, it came and hit it on the way up and on the way down, bounced back at that point of multiplicity. If a 0 has an odd multiplicity, so that would be like 1 or 3, you can be assured that you're going to cross the x-axis at that 0. All right. The next question looks a little bit tough, but I must tell you, this is probably the easiest one we have. It says to find the zeros of f of x if it's negative 4 times the quantity x plus 1/2 squared times the quantity x minus 5 cubed. Folks, this is already in factored form. And that means that in this, from this parenthesis, in order for this to all equal 0, because that's what you're doing when you find zeros, in order for that to all equal 0, then either one or both of those parentheses are going to have to equal 0. I can see right away that this negative 4 is not going to change anything. In fact, if I divided both sides of the equation, it would just go away. So the zeros in this one are, well, it would take negative 1/2 to get that, with a multiplicity of 2. And x is also equal to 5 with a multiplicity of 3. And since that's in factored form, that's quite simple to figure out. The last little hint for today, a table can help you to zero in on, she says, but really it just means focus in on those zeros. The intermediate value theorem sounds like it must be some big important thing, but it says if f of x changes sign, so if the value of y changes sign, then you have passed a 0. And if you think about that, it just makes sense. Think about here's an xy axis. If I have a function that's doing this thing as it goes along, right there, the value of the function changes from positive to negative. So I know that I had a 0 that's happened somewhere between the x's around there. Our next question, last one for the day, asks us to find the integers between which this function has zeros. So I am going to go back to my calculator real quickly here and set up a new page. My function is 3x cubed minus 10x plus 9, and I believe a standard viewing window will be good here. If it's not, we can always adjust. Ah, yes. Okay, so I'm looking at my graph, and it looks like there's a 0 that's really close in there between -2 and -3. You can verify that, of course, with a table. If we begin scrolling upward through this table, we will see that as you change from -2 on x to -3, the sign changes on y from positive to negative. Therefore, there must be a 0 encased in there. So, kind of a nifty little hint to help us find those zeros, and we could tell by looking at our graph, but also by looking at the table. So between -2 and -3, okay, we had a sign change. All right, that's the end of our lesson for today. I'm going to ask you to get to that U-try as quickly as you can, and hope you have a wonderful night.